The graph of the sine function. In this video, we're going to draw the graph of the sine function by finding some values for the function. First, let's recall the definition of the sine function. The sine function, denoted sine of theta, associates each angle theta with the vertical coordinate, i.e. the y-coordinate of point P, specified by the angle theta on the circumference of a unit circle. So in this picture below, we have a unit circle. So we have a circle with radius 1, and we have a point P specified by angle theta. And the definition of the sine function tells us that the y value, this height of point P, the y value is the sine value of theta. And this is if we put angle theta in standard position in a unit circle. The y-coordinate of the point specified by theta is the sine of the angle. So let's go back to our graphing platform. We've got a table where we can insert values and a grid where we can draw the graph. Okay, so first let's recall the association between the angles given in radians and their degree equivalent. You're going to want to memorize, internalize at least one fact to get yourself started here. And my suggestion is either to sort of memorize that 360 degrees equals 2 pi radians, or that 180 degrees equals pi radians. With either of these relationships, you can quickly discover all of the others. For example, if we were to take half of pi to get pi over 2, it must mean that if we take half of 180 to obtain 90, then 90 must be equal to pi over 2. And similarly, if we were to triple pi over 2 to make 3 pi over 2, that must be the same as tripling 90 degrees to make 270 degrees. So we can recall the association between degrees and radians through a system like this. What we'll do is plot points at these pi over 2 multiples, sort of 90-degree multiples as we rotate around the circle. Let's get scale on our axes. We've got 2 pi labeled here, and we can make all of the other labels adjusted to that. So half way closer to the y-axis must be pi. Half, again, closer to the y-axis must be half of pi, pi over 2. This tick then must be 3 pi over 2. And notice we get 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And we can just continue adding 1 pi over 2 to each tick. So that's 5 pi over 2. 6 pi over 2 is 3 pi. 7 pi over 2. And 8 pi over 2 is 4 pi. Now on the y-axis, we'll want to give scale for the y values that we'll obtain, the outputs for the sine function. Since we're rotating around a unit circle and plucking off the y-coordinate, the largest value we'll be able to get is 1, and the smallest is -1. The unit circle limits us from straying 1 unit from the origin. So our maximum and minimum y values will be 1 and -1, so we can get those labeled. Now we can go ahead and rotate around the circle to determine some values for the sine function and then plot those values to create a graph. So when the angle is 0 radians or 0 degrees, they're the same. We start on our angle in standard position along the positive x-axis, and we don't rotate at all. We rotate 0 radians. So we just land on the point that we point to directly there. Has coordinates 1, 0. And the sine function is the y-coordinate of the point specified by theta, by the angle. So the y-coordinate here is 0. So we discover that the sine of 0 is 0, and we can plot the point 0, 0 on our coordinate plane. Now we can move to pi over 2. We can rotate 90 degrees, pi over 2 radians. We end up pointing straight up to the top of the circle to the sort of north pole. And the point that we specify has coordinates 0, 1. The y coordinate is the sine value of this angle, pi over 2. We've rotated pi over 2 and found that the y value is 1. So the sine of pi over 2 must be 1. So on our graph above pi over 2, we can plot a dot at pi over 2, 1. Now we can rotate pi radians. Pi radians, 180 degrees, halfway around the circle. Specifies this point here on the sort of left pole of the graph of the circle. Coordinates -1, 0. The y coordinate is the sine value of the angle pi radians. So the y value is 0. Sine of pi must be 0. So we can plot the point pi, 0 on our graph. Now we can rotate 3 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 270 degrees. Point south to the bottom of the circle. Specifies this point here, which has coordinates 0, -1. This angle, 3 pi over 2, specifies the point 0, -1, whose y coordinate is -1. So the sine of 3 pi over 2 must be -1. So on our graph, above 3 pi over 2, we can plot the point -1 at -1. All right, now we can determine the sine of 2 pi. We rotate a full 2 pi radians. 2 pi radians, same as 360 degrees. Now we're specifying the same point we started with when our angle was 0. So we're specifying the y value 0. And so the sine of 2 pi must be 0. So above the point 2 pi, above the theta value 2 pi, we can plot the output 0. Now, from here, we can just continue rotating quarter revolutions. We rotate another quarter of the trip around a circle. Now we're pointing towards the North Pole again. The y value is 1. So the sine of 5 pi over 2 is 1. And so our output must be 5 pi over 2, 1. Rotate another quarter rotation. We're now pointing towards the left pole. The y value is 0 there, so the sine of 3 pi must be 0. So we can plot a height of 0 above the input value 3 pi. Rotate another quarter revolution. Now we're specifying the south pole. The y value is -1 there, so the sine of 7 pi over 2 must be -1. So at the theta value of 7 pi over 2, we can plot an output at -1. And go one more quarter revolution. We end up back at our starting spot. The y value is 0 there. So we can plot the height of 0 at the theta value 4 pi. So now all we need to do is connect these dots to get a graph of the sine function. Let's go ahead and clean up our circle a little bit. All right, so it turns out that the way we connect the dots is not like this. It doesn't. We don't end up with these pointy line segments that create the graph of the sine wave. We have to be a little bit more subtle about the way we connect the dots. Notice that as we're traveling around a circle, imagine you start here in standard position and you rotate around the circle repeatedly. Notice that the heights, which is what the sine function represents, right? The heights, the y values are what we're representing as we go around the circle when we're graphing the sine value. And notice those heights change quite quickly when we're at the left and right poles. The circle is shaped almost vertically there. Right, the curvature of the circle is not a lot different than a vertical line, and so as we're rotating around a circle and we're near angles that represent these like left and right poles, when we're in these rate regions, we're actually going to be traveling quite quickly. Our heights are changing quite rapidly. These are the areas when we're crossing the theta axis. In this area, we should expect the graph of the sine function to change quite quickly because the heights would be changing quite quickly if we were rotating around the circle. Compare that to the places in the north and south poles where the travel, if we were circling or going around a circle, the direction of travel is pretty flat here. We're traveling quite a lot horizontally, but almost no vertical change there. So we should expect the sine function to be kind of flat in these areas that represent the top and bottom of the circle because the heights aren't changing very quickly there. So it turns out the way that we need to connect these dots is in a kind of more curvy way. I like to draw each quarter wave separately. It allows me to get a pretty good graph. So just keep drawing these quarter waves. One coming backwards. And there we get a pretty reasonable picture of the sine function. This is the graph of y equals sine of theta.